Today we will be discussing how to save money with Fronius commercial installations. Does seem that we are having a bit of a problem to start with. So this is sorted out now. So welcome once again to our webinar today. Today we will be discussing how to save money with Fronius commercial systems. Today, our team for this webinar, I'm joined by my colleagues, Cyprian Okolo, who is our technical sales advisor based in Lagos, Nigeria. And my colleague, Mohamed Sidat, who is our technical sales advisor for Southern Africa, based in Johannesburg, South Africa, working from Fronius South Africa, a subsidiary of Fronius International. Our agenda for today, we are going to be looking at CAPEX analysis. Then we go into OPEX analysis. Later on, we look at energy yield for your system. And then we are going to have a detailed look at one of our reference projects operating somewhere in Austria. So we are going to give you an introduction into the owner of the system, then a system overview, then the consumption of energy in this system, and of course, what is the success behind it as far as the Fronius solution is concerned. And you're also going to look at how this system is monitored, or visualization of this system in SolarWeb. Later on, we are going to look at the commercial inverters available from Fronius for commercial systems. And just before we end, we are going to give you some more information on Fronius solutions and other products. Also, at some point in this presentation, we are going to launch a poll, and we would appreciate if you could take a bit of your time to give us some feedback on the question that will be asked in the poll. So to start with, we are going to be looking at the CAPEX analysis and then go on from here. So CAPEX, of course, refers to the initial system costs. And when you're talking about the initial system cost, of course, the inverter, the solar modules and all that are part of what is constituting the initial cost of the system. But when you talk about specifically about the inverter, the grid inverter, it's not enough to just consider the cost of that device alone, because that is not going to give you a very good idea if it's a fit or not for your system design. So the best decision is made when you compare all the incurred costs, the initial costs, as well as operational costs, plus the expected yields of the system. So for our particular example today, we are going to be looking at the Fronius Eco 27, and this is a Fronius 27 kilowatt inverter in 3-phase, and compare that to a 60 kilowatt competitor. So you can see here there is quite a difference between the output of the two inverters. In a single block, we have 27 kilowatts on one hand, and the other has 60 kilowatts. So quite a bit of difference there. So some more details into the example system that we are going to use for this CAPEX analysis. It's a roof-mounted system, and the total output is 408 kilowatt peak. That is on the PV side, and it is situated somewhere in Central Europe. So we can see a photo of the exact system here. So the details as far as the inverters are concerned, like I've mentioned, the PV generator is 408 kilowatt peak. The total output of the inverters is 360 kVA, and if this is on power factor 1, then this would be actual power of 360 kilowatts as well. And this is a cumulative figure of the 60 kilowatt inverters, for which we require 6 for a 408 kilowatt peak system. And then in comparison, we require about 13 Fronius Echo 27 inverters. So the overall CAPEX comparison looks like this. So we can see this pie chart to the left, and we can see the description of key parts. So you can see the modules here in blue are constituting the highest cost of the system, the initial costs. We have another portion here, 33%, which is constituted by the balance of system components, as well as labor, which is 14%, and associated costs with labor. That means also probably logistics and stuff like that. And the inverter, the cost is one of the lowest as far as the CAPEX is concerned, at 9% of the initial total cost. However, even though the inverter is costing just about 9%, it has a big impact on the performance and the eventual return of investment from your system. The balance of system components at a much higher percentage of that 3%. We are going to look at how an intelligent system design can influence the cost as far as the balance of system components are concerned. So therefore, CAPEX is an important factor when you are determining your return of investment, because initially when you're going to give a proposition to a customer for a potential system to be installed, then you have to work out what is the expected return of investment period. So this is one of the very important factors for your installations. In terms of the balance of system costs, in most cases, these are costs that are not related to the inverter or solar panels, or the inverter and the solar panel have a very small effect on the actual costs on the balance of system components. And these are accessories such as racking systems, cable trays, main grid connections, etc. Because if you do have like a design where you require 200 kilowatt peak, or for a particular example of 488 kilowatt peak, the racking system, the cable trays and all that will primarily remain just enough so that you're able to install the desired system size. So the inverter itself would have an effect on the AC-DC cabling, as well as AC and DC distribution boxes. With the right system design, by choosing the right inverter, you can make really big savings for your system. And this analysis we are going to be looking at later to see what are the effects of choosing the right system for your particular design. Of course, like I mentioned, is based on our Echo 27 and the competitor 60 kilowatt inverter. And you're going to be looking at examples of both a centralized and decentralized systems. So let's get into the inverters to help us understand the effect of the right inverter on the balance of system components. And this particular illustration here, to start with, we are looking at a centralized system configuration for a Fronius Echo 27 inverter. What we should pay particular attention here to are the distances from the modules, then to the string combiner boxes, and then the distance from there, the string combiner boxes to where the inverter is, as well as the connection now from the AC side to where the load consumption point is, or the grid feeding point is. So in this particular example, we can see that the DC cabling from the panels to the inverter are running a much longer distance of 45 meters plus 80 meters in comparison to the AC side of the cabling that is running only approximately 20 meters from the inverter to the feeding point. So in effect, therefore, our string combiner cost here is about 120 euros, so times 13. So cumulatively, if you do the cost of the DC side, that is the string combiners and the DC cabling, plus the cost of the AC combiner box and the AC cabling side, you will come to a figure of about 7,753 euros for this particular example. So the strings are collected, of course, in the string combiner box, and only two DC cables are running from the string combiner box to the inverter. And therefore, this cabling, you can see the difference here. When you are starting with a string, you are coming out with a 6mm cable. And then when you come from the string combiner box to the inverter, the thickness of the cable increases significantly, and we are dealing with a 35mm cable. On the AC side, from the inverter into the AC combination box, so this is where each inverter is taking its AC output. You're coming out with 16mm cabling, but when you're going to the feed-in point or the consumption point, then also the cable size is increasing significantly to 70mm square. In comparison, let's look at the 60 kilowatt competitor that we are comparing this setup with for BE balance of system costs. So the average distances are almost the same, with a slight increase for the panel to the string combiner section here. And the AC distances remain pretty much the same. So you can see the cable cross sections have remained the same at 16mm square and 70mm square. Here, the big difference is the 70mm square cables. With the Fronius Eco 27, we used 35mm cable. And here with the Fronius Eco 27, we had string cables of 6mm square diameter. As a result, if we do the combinations here of the combiner boxes plus the DC cabling as well as the AC combiner box and the AC cabling, we are coming to a figure of about 9,816 euros for a centralized system using a 60 kilowatt competitor inverter. So, and the key difference in cost here is being driven by the cable cross sections used, as I have highlighted. Of course, also the combiner and the distribution boxes are affecting the total balance of system costs. And you can see the actual difference here when you compare the Eco 27 kilowatt inverter in a centralized configuration with a 60 kilowatt competitor inverters for the same configuration centralized. The Eco is coming out at an advantage of about 2,663 euros. And therefore, this is a cost benefit that can also be transferred to your customers, or when you are bidding for a competitive project. And with the proper design, you can easily be able to offer a cost advantage of up to 2,000 euros when you're using the Fronius Eco inverter in comparison. So let's now look at a decentralized system setup. And this means the opposite. So in our centralized setup, the DC cabling was running for a much longer distance than the AC cabling. But in a decentralized setup, the AC cabling on this side is running a much longer distance than the DC side. So you can see a cumulative distance of the AC side of about 100 meters. So considering from the inverter to the AC combiner box, we have 10 meters. And then from the AC combiner box to the feed-in point or the interaction point, we have about 90 meters. So that's about 100 meters on the AC cable and just about 48 meters on the DC cabling side. So in this example, using the Fronius Eco 27, we are running string cables using only 6mm square cross section. And then from there, we run into 16mm cable for the junction between the inverters and the AC combiner boxes. And then from there, we are moving into a much bigger cross-section cable of 240mm square from the AC combiner boxes to the feed-in point. And for this configuration, the total, when you cumulatively add all the components or the balance of system components that you require with the Fronius Eco inverter, we are coming to a figure of about 6,923 euros. So the key difference here, of course, to note is the AC cabling is much thicker in diameter. In comparison, we look at the 60 kilowatt competitor inverter and approximately the same distances on the AC side of about 100 meters. But we have slightly longer distance on the DC side. So it's about 65 meters with 10mm square cables. The junction from the inverter to the AC combiner is still the same with 16mm square, and the AC combiner to the feed-in point, we have 2 by 240 millimeter square cables. So if we add this total of the balance of system for this particular setup, we are coming to a figure of about 10,327 euros for the competitor inverter. And therefore, the Fronius Eco inverter in this kind of setup is giving you a cost advantage of about 304 or 3,400 euros in comparison to the competitor inverter. And this big difference is cost, of course, is being driven by things like surge arresters, AC fuses, and DC boxes that would be required comparing the Eco and the competitor inverter. So also here, the Eco is giving you a much higher cost advantage as far as CAPEX is concerned. Let's now proceed and look at what this means in terms of the actual cost advantage comparing the two system setups. So in red here and the faint red here, we have the comparisons for the Fronius Eco. So this is the central setup, and this is the solid red line here is showing the decentral setup. So we are taking the decentral setup as the base cost for comparison because this has offered us the least configuration cost, considering a distance starting from 50 meters. So if you are to extend this distance going further up to about 150 meters, you can see for the two system configurations using the data that I've shown you before that the Fronius Eco will offer you a 62% cost advantage as far as the balance of system components are concerned compared to the 60 kilowatt competitor. And therefore, this is really something that you should think about when you are designing your systems and ask yourselves the question, does it always make sense to use a big inverter? So for especially rooftop installations, where the effort to take the inverter into the roof, especially when the inverter is quite heavy, is a lot more compared to a lighter inverter. And you're also going to look at these details, how the effect of weight on BOS comes in later in the presentation. So in summary, what we can mention as far as the balance of system costs are concerned is that there is a huge effect on the distance of the cabling from the PV modules to the point of interaction. Of course, that means that will have a direct effect on the cable cross-section used. Also, another differentiating factor would be, are you designing a central or a decentralized system? And we've seen that a decentralized system using the Eco is giving you a much higher price advantage as far as the BOS components are concerned. And for our particular example, where we are talking about a 408 kilowatt peak system, rooftop system, there is a 62% clear benefit advantage when you're using the Fronius Eco, as I've mentioned from the previous graph. So therefore, you can see a significant cost advantage with the Fronius inverter in this case. So let's now get into another important aspect of consideration when you are designing or projecting how effective or how cost effective your system will be, and this will be the OPEX analysis. In short, OPEX are costs that are incurred in the day-to-day or day-to-day commercial operations of the system. And this will include both the planned and the unplanned costs as far as service is concerned. In terms of the major service activities that can be planned for your system, this would include module cleaning, cable connection inspection. This has to be done from time to time for sure. You want to be sure that all the DC combiner boxes and the AC combiner boxes, the cable connections are always firm so that you don't have potential for arcing and things like that. Also, cleaning of the inverter cooling system is also an important consideration for OPEX. And that comes into play when you're also discussing, is it an actively cooled inverter or a passively cooled inverter? And we are going to look at what are the key differences when you have an actively cooled inverter and a passively cooled inverter. Also, you might be interested in taking the voltage and current measurements of your PV system just to make sure that these are within the expected thresholds. And if not, then something needs to be done to correct it. So in terms of the Fronius advantage as far as OPEX is concerned, Fronius, of course, all our inverters are actively cooled, and we are going to be comparing with a passively cooled competitor inverter. But when you're talking about a passively cooled inverter, we are talking about an inverter that you require more maintenance or service efforts. This includes cleaning of the cooling fins to prevent yield losses from accumulation of dust on the fins themselves. But also something worth to mention here is that, as you may know, some of you may know that we have a very simple service concept with our inverters. It is possible to replace our PC boards very easily on site, and therefore only one person is required for this kind of service. But with a competitor inverter, for instance, if you're talking about a 60 kilowatt inverter, the weight itself does not allow one person to work on that particular inverter. And when you have to bring the entire inverter down for service or replacement, then you have to arrange for much more manpower. Maybe a crane is required to bring the inverter down. And therefore, as an OPEX, this is a huge cost that you have to think about and be aware of. For this particular analysis, we are talking about, of course, this passively cooled inverter with a Fronius Eco 27 that is actively cooled. And we have analyzed quite a number of things that need to be done from time to time. So we start with the scheduled maintenance, and then we also look at number of service callouts that are possible. That is something that you have not planned for the passively cooled inverter, as well as scheduled maintenance and service callouts for the Fronius Eco 27. And you can see that the number of visits per year for the passively cooled, like I said, with a passively cooled device, you need to think about cleaning of the cooling fins to avoid accumulation of dust. So therefore, minimum 2 visits per year. With a Fronius Eco inverter actively cooled, of course, it's able to blow away some of the dust on the heatsink itself. But if you need to check on the cooling system, maybe 1 visit per year is required. So number of people that will be required to go on site for scheduled maintenance for the passively cooled is 1 person, then 2 people for the service callouts, and then in the same case, we need only 1 person for whichever case with a Fronius Eco inverter. So in total, once we look at all this information, the total cost as far as OPEX for the passively cooled inverter is about 1,800 euros and 720 euros for the Fronius Eco inverter. So therefore, looking at these 2 figures, you can see a clear cost advantage of about 1,000 euros in annual savings when you're using a Fronius Eco inverter for this particular example. Now let's go into another important aspect of your design as far as the system is concerned, and this is the expected energy yield. So what we have talked about so far, the CAPEX and the OPEX, the comparison of that only are not enough to determine how cost effective your system is. So for you to be able to know how effective your cost effective your system is, you have to look at what is the expected energy yield over a given period of time. And this is going to inform also on your inverter choice. So expected or actual energy yields are used to determine the return on investment as well as the localized cost of energy. And a simple formula for determining the localized cost of energy is CAPEX plus OPEX divided by expected yield over a given period of time. And of course, the localized cost of energy is given in cent euro or cent currency unit per kilowatt hour. So let's now look at a very specific comparison between a Fronius Eco 27 actively cooled and a passively cooled 33 kilowatt competitor. So as a result of the derating behavior, what kind of effect do we expect from that, from these two comparisons? And our analysis is based on an independent tool, that is PVSYST, also focusing on our 408 kilowatt example. So, and we can see very specific energy yield data for the two inverter types. And with the Fronius Echo, we have about 1,273 kilowatt peak per kilowatt hour per kilowatt peak installed. And then for the passively cooled device, we can see there is a slight difference of 1,222 kilowatt hour per kilowatt peak installed. And therefore, if you compare the two figures, we have a slight advantage of plus 4.17% in comparison to the Fronius Echo. So the Fronius Echo in this case is giving you more energy. And these are the compared site conditions, so operating conditions of the modules and the temperature on the inverter as well. So in terms of now the energy yield analysis itself, we are talking about savings from the data given below, and looking also at a projected period of 15 years. And as we know, our systems are expected to operate for something like 25 to 30 years. But this projection shows us for the two categories of inverters, the 33 kilowatt active passively cooled and the Echo actively cooled, with this kind of output per year, and then a possible feed-in tariff of about 7.9 cent euro per watt hour, or per kilowatt hour in this case. So we look at this cost advantage or yield advantage with the Fronius Echo 27. And you can see that over a 15-year period, so the red line here represents Fronius, and the gray line here represents the 33 kilowatt passively cooled competitor inverter. And over a 15-year period, we can see a clear advantage here of about 41,000 euros in earnings of the Fronius inverter compared to the competitor passively cooled. So also now, when you do your system simulation using professional tools such as PVSYST, you can see clearly which inverter choice you should go with. And therefore, we always recommend that you use an actively cooled inverter, because even the derating behavior when the ambient conditions are above certain thresholds are very different on either a passively cooled inverter, which derates earlier, compared to an actively cooled inverter. In our cases, the inverters can start derating or with start ambient temperatures of up to 50 degrees Celsius. Okay, then, so I think we are done with our first part of the presentation. What I would like to do at this point is to launch a poll, and as I had mentioned in the beginning, we would appreciate if you could take your time and give us your feedback on this poll, so that we can get an idea which kind of system you are mostly installing. So the poll question is, what is your average installation capacity? And we have a few choices. We have 4 choices here, 5 to 50 kilowatt peak, and then up to 100 kilowatt peak, then from there up to a megawatt peak, and above 1 megawatt. So I will leave the poll on for the next 20 or so seconds, and then I'll close it and share the results with you. And then after that, I'll be heading over to my colleague Cyprian to continue with the next session of this webinar. So thank you so much for everyone who has given us your feedback on this poll question. So I'll be closing it now. Then I'll share the results with you. And we can see that in our audience today, a lot of you are doing systems in the range of 5 to 50 kilowatt peak. Another considerate number are doing systems up to 100 kilowatt peak. And therefore, when you start talking about commercial installations, it's good to see that we have a good audience here that is doing commercial installations. But that does not mean that we do not appreciate those guys who are doing even smaller systems. At Fronius, we focus a lot even on smaller rooftop systems, and we're giving a lot of focus on that by giving you smaller rated inverters, even starting from 1.5 kilowatts. So even for bigger systems, this is quite okay. And thank you so much for giving us your feedback on that. So at this point, I would like to hand over to my colleague Cyprian to take over and show you one of our key reference projects that is working in Austria. Cyprian, please join from here.
Yeah, thank you very much, David, for that very wonderful presentation. It was quite descriptive and very well detailed. So I will be continuing with a reference project because that will serve as a good example to buttress the fact and, of course, importance of making the right choice in terms of inverter selection. Okay, so we're going to take a reference here from an organic food retailer. His name is PICHLER, who runs the company Biohandel. It's a family company, family-owned company that has been in existence since 2007, and basically deal with organic fruit and vegetables. So it has a total storage space of 1,300 meters squared. Part of this, 650 meters squared is used for cold storage, and then 300 meters squared is used for parking station, office, and hall. And then, yeah, so that's basically it. Also included is a fleet for the company. It's actually an EV fleet, electric vehicle fleet, to help in transportation. And then, of course, since it's an organic fruit and vegetable company, of course, there will be need for machines to process these variables. Great. So to have a quick system overview, we have the system data, and then the system size is approximately 100 kilowatts peak, 99.9 to be specific. It's a roof-mounted installation, as you can see in the picture beside the information. It was commissioned in July 2018 with an annual yield of 100,000 kilowatt hour, and self-consumption rate is quite high, 80%. Another processing company, so it will require facilities for cooling. So we have cooling, transportation, like I told you, they have a fleet of vehicles, EVs, and then we have processing machines, office infrastructure, and then of course some lighting points. So these constitute the major consumers within the system. And a look at the load profile. It gives you a detailed information in terms of the reactive power, the real power. And from here, we can see that it goes into a very, very high region of about 200,000 kilowatt hours. So breaking that down, the real energy daytime consumption is 152.156 kilowatt hour, and then the real nighttime energy consumption is 48.787 kilowatt hour. So of course, summing up to about 201,000 kilowatt hour, and then the power consumption is 64.8 kilowatt. So of course, you have the details for the reactive power. So with this information, the next question to ask is, okay, given the situation on ground, how much energy could be saved for using a Fronius best solution? So after the commissioning, installation, and a period of usage, we came to conclusion that a total of 10,000 euro annual savings can be achieved with 80% self-consumption, 40% degree of self-sufficiency, and a remarkable amortization period of 5 to 6 years. So how did this come about? So which Fronius solution was responsible for this success? So as you can see, the picture beside is a picture of the installation. So we have 3 number Eco 27s, 1 number Fronius SIMO 6, and then of course a smart meter, which is obviously installed inside the box. So for the system design, we have the technical details of the respective inverters used. So for the Fronius Eco 27, which of course implies that it's a 27 kilowatt inverter rated. It has one FP tracker, protection class of IP66, and a weight of 35.7 kilogram. This input range is 580 to 1000 volts. I want us to take note of this weight in particular because we're going to make reference to it in the subsequent slide. So for the SIMO, it's a 6 kilowatt inverter, multiple epic tracker, IP65 protection class, weight of 19.9 kilograms, and DC input power range of 150 to 1000 volts. Yes, so point of note is that the data manager, the Fronius SIMO here is the one that carries the data manager. So it's the full version that has the data manager, while the Echoes are the light versions without the data manager. So as we all know, just one data manager is enough for this particular system. So the communication will go via the data manager installed inside the SIMO 6. Great, so this is basically a single line diagram to demonstrate how the system was implemented. On the PV side, 30 kilowatts channeled to the respective Eco inverters, Eco 27 inverters, and then approximately 10 kilowatts was now connected to the Fronius SIMO 6 inverter. And then all there's change to supply the needs of the load consumption point via a Fronius smart meter. Yes, point of note here also is that as you can see, on the PV side, we have 30 to 27, 30 on the PV side to an Eco 27. Just to reiterate the fact that for our small devices, like in this case, our small SIMO, that was used in this case, it can actually be overdimensioned up to 200%. And then for the Echo, the maximum overdimensioning range is put at 150%. So just to inform you of this very valuable information. Great, so we've seen how the system was implemented. So now let's look at how it can, or it was, or is visualized on Fronius SolarWeb. So as you can see, with the picture of the site, and then we have the details of the energy balance for consumption and production, and very importantly, earnings for the day. This doesn't stop here. You can also have an overview of your earnings per day, per month, and overall since the system installation. And of course, have the information of how much CO2 we have actually saved. And very importantly, you also have the weather widget to inform you of how the irradiation is and help you in taking some informed decisions when it comes to the usage of the generated energy. So to give us a clear and a much more precise effect of this installation, we decided to pull out one day info, one day chat to give us a much more detailed explanation of what is going on in the system. So for this particular day, which is the 30th of March 2019, we achieved a self-consumption rate of as high as 84%, The production on this day was 498,089 kilowatt hour, and then the amount of energy consumed directly was 420,022 kilowatt hour, 420.22 kilowatt hour. Production was 498.89 kilowatt hour, and then the power to the grid, very important. It was a meager 78.67 kilowatt hour, so which was quite minimal, if I'm being honest. So, and doing an annual comparison, we can now see that for 2018, we had a production of 35.69 megawatt hour. Out of this, 28.94 megawatt hour was consumed directly, and a meager 6.75 kilowatt hour was channeled or fed into the grid. So this, of course, shows us how effective the installations were to, first of all, increase self-consumption and, of course, independence. Same also can also be applied or as seen in the case for 2019. As you can see, the comparison between self-consumption rate and energy that was fed into the grid. So that being said, we're going to look at a part of the food retailing, the organic food retailing organization set up by PICHLER, which is the e-mobility, from which he was able to also save a lot of money. So in his company, he has a fleet of vehicles that's basically used for transportation. So we have a BMW i3, e-Golf, a Tesla Model 3, and a Tesla Model S. So these 4 vehicles are actually put in use for transportation purposes. Now, another thing you can now ask, okay, how fast can you charge on the company premises? So with this, we have to look at 4 basic factors that contribute to determining how fast you can charge from their company wall boxes. So first of all is the PV system size, generally speaking, and then of course the capacity of the grid connection, which have all been taken care of. So another thing we should consider is the output power of the charging station, and then the onboard charger of the EV. So we're going to look at these 2 factors in much more detail. So for the charging boxes installed in this company, we have the IKEBA P30 wall box and then the Tesla wall box. So he implemented the IKEBA to charge the BMW and the Golf, and then the Tesla wall box to charge the Tesla vehicles, the Tesla Model 3 and then Model S. Okay, so we're going to look at the detail of these wall boxes. So for the IKEBA, it's of course a 3-phase with a 32 ampere current capacity and then maximum power output of 22 kilowatts. Of course, like I said earlier, used to charge the BMW and the Golf. So for the BMW i3, charges up to 11 kilowatts, and then for the Golf consumes 7.2 kilowatts. But this is of course dependent on the model of the charger being used. And then for the Tesla wall box, it's a type 2 plug, 3-phase, 32 ampere current carrying capacity, and the maximum output of 22 kilowatts, and used to charge the Tesla with 11 kilowatts. That is for the Model 3, and then the 16.5 kilowatts for the Model S. Great. So how is now this PV loaded into the fleet? So how was this designed? So initially, there's no intelligence control, no dynamic charge regulation, as it is in this case. Of course, it's going to be done eventually. So, but at the moment of doing this research, the dynamic charging regulation has not been implemented. So we'll always advise or recommend from Fronius that the implementation of an intelligent charge control, which will of course help in adapting your charging with of course the programmed data manager to a set of fixed figure, as we discussed last 2 weeks when it came to maximizing self-consumption, for those that attended the webinar last 2 weeks. So invariably, we have recommended Hadibath e-charge CPH1, as you can see here. This has already been tested with Fronius and is a certified wall box to be used, and that of course would achieve and attain an intelligent dynamic charge control. So in this regard, we decided to pull up data for EV charging on the 20th of June 2019. So we can see on this day a production of 620.66 kilowatt hour. The day where we had 71% of self-consumption. 427.95 kilowatt hour was consumed directly, and then power to the grid was 192.71. So in this case, with a dynamic charge control wall box, we can implement and program this wall box to automatically charge vehicles connected or plugged into the system. This will be seen in the simulation, as can be seen on the next slide. Yes. So let me go back one slide to give us a narrative to this slide. So as we can see, there are periods of when power was fed into the grid up to a volume of or capacity of 192.71. So this part of the energy can, instead of being fed into the grid, can also be channeled to charge the electric vehicles. So as you can see from this simulation, the simulation that was done with this same data, we can see that on the 16 kilowatt charging block, we can have as much charge as 193 kilowatt hour, which is equivalent to 1,100 kilometers mobility per day. So if this is implemented, you can have your vehicles charging this free or excess energy that is being fed into the grid, and of course you can now achieve this capacity of charge, and then of course that's in turn translates to 1,100 kilometers mobility per day, which is actually a good one. So in effect, it means that for this company, by PICHLER, the connection, disconnection was actually done manually. So just to clarify that. Yeah. So in order to do this automatically, like I said earlier, Fronius recommends the Hadibath charging, EV charging wall box. Control is done via the data manager, the Fronius data manager, and of course it has quick charging and makes use of the PV surplus energy to charge your EV as programmed. Exactly, as programmed. Yes. So as you can see, we have a single line diagram of how the connection is done. You have your power cables connected to the charging point, and then the communication done via a router, and that is it. The charging comes forth automatically, well adapted to your excess PV generation. So this is, of course, exemplified here, as you can see. Like I told you, based on the programming that has been done on the data manager, it will now infinitely variable. You can now achieve infinitely variable control of your charging capacity dependent on the PV surplus power. So energy management has already been integrated via the integrated controller, and of course the communication, as was seen or as has been seen in the last slide, yeah, is done via LAN or wireless LAN, or variably called the Wi-Fi. So Summary and prospects for the future. So as you can see from this example, the future is obviously very, very bright. We're able to save 10,000 euros yearly, which translates to about 833 euros per month. So if you convert that to your local currency, you can see that it's quite a lot of money. Yes, it involves a good or a considerable CAPEX, like my colleague David has earlier said, but in the long run, after 5 to 6 years, you have recovered from the expense, the initial expense, your CAPEX. So with this, we're able to achieve 80% on the average self-consumption rate. Degree of self-sufficiency was 40%, and then mean supply gotten in this system was 60%. Yeah, so we've talked about the example, a reference case where the system was implemented. So let's give us an overview or a brief. I know we all know this. Most of us have an idea of this Fronius commercial inverters. So it wouldn't hurt to still go over them again, the inverters responsible for this success. So they're basically Fronius big inverters that range from 10 to 20 kilowatts power range, and then Echo 25 and 27 kilowatts. So they're basically used for medium, large scale systems of above 50 kilowatts, and of course running into the megawatts range. We have I think our largest installation so far in Ukraine of a capacity of about 52 megawatts, all implemented by the Fronius Echo. So the features of these inverters includes a high flexibility in design, no additional components needed as in case of a DC combiner. So in a case where you're using a centralized system, of course, you don't need a DC combiner. You can just connect all your systems directly. We have the possibility of using only one master inverter for several systems as connected on the solar net. So one data manager can actually carry up to 100 inverters, but then for practical purposes, and then of course for ease of communication, and of course to minimize latency as much as possible, we tend to recommend one data manager per 20 to 25 inverters. So of course, by so doing, this is very cost optimized solution. And then just to give us a highlight on the high flexibility in design, in a case where we want to implement, say for this example we discussed, 100 kilowatts peak system. If you noticed, we used 3 number of Echo 27. Total sum of capacity gives us 81 kilowatts, and then 1 Simon 6, which now gives us a total of 87 kilowatts. And with an oversizing percentage of 115, we're able to have a very good inverter ratio between the DC side and of course the PV generator and of course the inverters. So it gives you that flexibility of combining inverters to achieve particular energy or particular capacity as capacity or targets as required. Yeah, so giving us a brief on the characteristics of this technical details of our inverters. The big Simons range from 10 to 20, as can be seen. It has 2 MPP trackers, and of course, like I explained already, it has a Superflex design. Talking more about the Superflex design, there are inverters that are actually designed to carry equal number of equal capacity on both MPP trackers. So some design it for 50-50 purposes, and then while some are designed to carry more power or more capacity on one MPP than the other. So, but in our own case, in the Simons case, we have all these integrated into one inverter. So be it equally proportioned, that is 50-50 or 40-60 or 80-20, our inverters are well designed to actually adapt to these varying options of orientation. Yeah, so that's for the SIMO. Then for the ECHO, which is fondly called the commercial or the project inverter, so we have just two classes, the 25 and 27 kilowatt power class. Like I said, it's optimized for commercial purposes and then has one MPP tracker. So, of course, in order to aid design and implementation, we have various accessories, various options of accessories. We have the overvoltage protection, which is called the SPD, surge protection device, or the overvoltage protection type 1 plus 2 or type 2, and implemented for the SIMO 10 to 20 and the ECHO 25 to 27. We have the DC connector kit. So in the case where we necessarily need to use combiner boxes, you can now use this DC connector kit to implement this and then have two bigger sized or larger dimension or cross-sectional areas of cables of up to 25 mm squared or 35 mm squared. And of course, we have string fuses recommended, 15 amp fuse per 1000 volts. And these fuse holders are already integrated into the ECHO 25 and 27. So in terms of power output per unit weight, our inverters tend to lead the way. So I told us earlier that we're going to make reference to the weight of the ECHO. So we have a comparison here between the ECHO, the Fronius ECHO, and 3 other competitors. Same power output, but different weights. So this obviously means that in terms of weight, our inverters are lighter. It invariably means that it is more economical and of course much more efficient in terms of power output per unit weight. And also in addition, because our inverters are actively cooled, like my colleague rightly pointed out earlier, we tend to have our inverters tend to withstand ambient temperature of as much as 45-50 degrees Celsius before the rating sets in. When compared to our competitors that are passively cooled, the rating begins much earlier, as low as 30 degrees Celsius. Yeah, so yes, we have a big information for you here. We are going to have a quiz webinar coming up on the 22nd of October. And what makes this quiz webinar very special is that all the questions that are going to be asked on this day will be drawn from the webinars we're going to run from today until the Thursday before the 22nd of October. So we're going to run 6 webinars before the 22nd of October. So all the questions that are going to be asked will be drawn from these respective webinars. My colleague, Mohammed Sidat, is going to upload an information for you, which I can tell you that has information about the respective questions we will be asking on that day. So, and graciously enough, and we have a wonderful prize that is going to be won on that day, which is a Primo, a Fronius Primo inverter will be won on that day. So all you need to do is to register for these webinars, attend them, become a Fronius Solar Expert, answer the questions correctly, and the person that answers the most correct questions wins the prize. So once again, it's coming up on the 22nd of October, same time that we always have our webinars. So I'd want us to look out for this, more attentive in our webinars, and pretty sure that you stand a very, very good chance of winning this wonderful prize. So that is the length of our presentation for today. If you have any inquiries, technical questions, you can direct them to our technical team. Sales, any question regarding sales, trainings, and after-sales service, you have all the information that can be seen on the screen. Or better still, you can contact us directly. Contact my colleague who is in charge of the Southern African region, Mohammed Sidat, David Mwangi for Eastern Africa, and myself, Cyprian Okolo, for Western Africa. So that is the length of the presentation today. I hope you all enjoyed it and got most of the information you were looking out for. So at this point, I'd like to invite my colleague, David, to see if there's